Good morning and welcome to this presentation. I am Ali Kalfala from SEMPR at the Department of Mechanical Engineering at the University of Coimbra. Today I will present our research titled Intelligent Approach for Accurately Identifying Constitutive Material Parameters of Anisotropic Tubular Materials. This work focuses on addressing challenges related to the mechanical characterization of anisotropic tubular materials, particularly in the hoop directions. Our research integrates advanced methodologies, including surrogate modeling, finite element simulation, and artificial neural networks to optimize the specimen geometry for specific tensile tests labeled the Ring Hoop Tensile Test, or RHTT, and then use it to accurately identify anisotropic tubular materials parameters. So let's start by understanding why this research is important. Tube metals and anisotropic tubular materials play paramount roles in various sectors of industry, including automotive, aerospace, and nuclear power. Specific applications include fuel cladding tubes in nuclear reactors, complex parts formed through tube draw forming processes in automotive manufacturing, and tube drawing bending operations essential for aerospace components. So, to master these complex tube metal forming processes, accurate mechanical characterization of tubes is essential for reliable simulations and for predicting potential failures during service. But what makes the mechanical characterization of these tubes so challenging? Anisotropy in tubular materials originates from their manufacturing processes such as cold or hot extrusion or sheet rolling followed by welding, which produce a curved geometry and particularly a cylindrical form with directional mechanical behavior dependence that make their comprehensive mechanical characterization using traditional methods difficult. So, identifying constitutive parameters of anisotropic tubular materials presents significant challenges due to complexities in the cylindrical geometry, which prevents cutting samples in various directions as we can do with sheet metals. Moreover, traditional methods such as flattening tubes for tensile testing introduce substantial residual stresses and pre-strains, as you can see in these illustrations, where we show here the tensile test of two specimens cut from the same materials, but the first one is obtained after flattening, is cut after flattening the tube, and the second one is obtained after cutting a tensile sample along the axial directions. So these testing artifacts particularly compromise measurement accuracy in the hoop direction, which significantly influences component performance. These led research to develop alternative testing methods for mechanical characterization of tubular materials. The Ring Hoop Tensile Test. It offers a promising alternative for determining mechanical properties along the hoop direction without disruptive flattening operations, as you can see here with the experimental setup. Therefore, evaluating the mechanical property of the as received metallic tubes. While Ring Hoop Tensile Test addresses some problems, it introduces its own set of challenges that need to carefully considered. Despite its advantages, the Ring Hoop Tensile Test technique presents three key challenges that must be addressed systematically. First, achieving homogeneous stress and strain distribution within the test specimen's gauge section is difficult due to non-optimized sample geometry and frictions. As you can see here from these illustrations, where we used finite element simulation by varying different geometries. Second, quantifying the unavoidable friction between the sample and test fixtures requires special considerations. And third, we need robust methods to accurately identify the true material parameters from the test data, separating them from testing artifacts. To address these challenges, let's first have a look to a brief review of literature that highlights the attempts of research over many years to refine and improve the design of an appropriate ring hoop tensile test method for the mechanical characterization of tubular materials. This table exposes a comprehensive overview of various ring hoop tensile test configurations with different tube dimensions and utilizes numerous materials including aluminum alloys, zircaloy, and steels. Despite these advancements, it is revealed that several persistent issues haven't been adequately resolved. First, various specimen geometries have been proposed without comprehensive validation or justification for the chosen dimensions. Second, the critical assumption of uniaxial stress state within the gauge section often remains unverified. And third, the significant effect of friction between the mandrel, the fixture tool, and specimen is frequently overlooked or inadequately evaluated, yet it substantially influences the results. To address these gaps, we developed a comprehensive methodology with two main components, as shown in this flowchart. First, we focus on optimizing the ring hoop tensile test specimen geometry through the development of a surrogate model, including design of experiments, finite element simulation, and response surface methodology to achieve homogeneous uniaxial tensile state. Second, using experimental data from tests with the optimized specimen, we employ an intelligent inverse analysis combining finite element simulations with an artificial neural network to simultaneously identify both the true material parameters and the coefficient of friction, and this is what stands for our objective in this work. Let's examine the specimen optimization process in more detail. For our case study, using aluminum alloy tubes with 50 mm outer diameter and 2 mm thickness, we define three key geometric design variables, namely the gauge length, the width, and the fillet radius. Our optimization targets aimed to achieve a stress state of uniaxial tensile test by targeting specific values for strain ratio, stress ratio, stress terrestriality, and load parameters, as listed here, with their ideal values. These values represent the ideal isotropic uniaxial tensile test that we want to achieve in our testing. To explore this design space effectively, we implemented the structural design of experiments approach. We used a full factorial design of experiments with 2 levels for each of our 3 variables, resulting in 8 distinct specimen geometries that needed to be evaluated numerically. This approach allows us to understand both individual and interactive effects of each design variables on the resulting stress state. Each of these 8 designs was then evaluated through detailed finite element analysis. Our finite element analysis was conducted using abacus standard, exploiting symmetry. Half of the setup was modeled for computational efficiency. We used deformable 3D solid elements for the ring specimen within 5 elements through the thickness and rigid shell elements for the D blocks. The material model assumed isotropic elastoplastic behavior with swift hardening and an associated flow rule for this optimization phase, while contact between the ring and the D blocks was modeled using master-slave approach with column friction and a representative coefficient of 0.08. The results from these simulations provided the basis for our surrogate modeling and optimization. Using simulation outputs, we developed response surface method models, essentially regression equations, to predict our target outputs based on the geometric variables. The extremely high R-squared values, exceeding 99% for all responses, indicate excellent model fit. We then applied a multiple objective desirability optimization approach using Minitab's response optimizer, which yielded an optimal specimen geometry with gauge length of 16 millimeters, width of 3.8 millimeters, and fillet radius of 6 millimeters, achieving more than 81% composite desirability. With this optimized geometry defined, we proceed then to the experimental testing phase. We conducted experimental tests using specimens machined to our optimized dimensions via electrodischarge machining. The testing campaign including standard uniaxial tensile tests along the tube's axial directions, 0 degree, which provide the reference properties and the Langford coefficient R0. We also performed Ring Hoop Tensile tests, and stereo image correlations is used to strain measurement, yielding to Langford coefficient R 90 degrees for the hoop direction. However, friction between the specimen and test fixture complicates direct perforated extraction, necessitating our intelligent inverse analysis approach. This flowchart details our intelligent inverse identification procedure for simultaneously determining material parameters and the coefficient of friction. We start by defining the plausible ranges for the unknown material parameters, the yield stress Y0, the strength coefficient K, and the hardening exponent N, and of course the coefficient of frictions. We then use design of experiments and finite element simulations across these ranges to generate a database linkage these input parameters to resulting ring hoop tensile test force displacement curves, which serves as training data for our artificial neural network. Let's look at the specific parameter range used for generating this training data. To train our NN effectively, we generated input data through numerous finite element simulations that systematically varied for key parameters: the yield stress, the strength coefficient, and the strain exponent, and the coefficient of frictions within the range shown in this table. This ensures the network learns the complex relationship between these inputs and the resulting force displacement response across broad spectrum relevant to our experimental data. The network architecture was carefully designed to handle this complex identification problem. We implemented the feed-forward artificial neural network with an architecture comprising 3 layers: the input and the hidden and output, as shown in these illustrations. Through a trial and error optimization process, we determined that 10 neurons in the hidden layer with a learning rate of 0.01 provided the optimal performance using mean square error as our performance metrics. The network takes discretized force displacement data points as input and output for the 4 parameters we seek to identify: Y0, Kn, and the coefficient of friction. Now let's examine the key results obtained through this methodology. First, validating our specimen design optimization, finite optimization using the optimized geometry clearly demonstrate success as shown in these contour plots. We achieved a homogeneous distribution of both hoop strain and hoop stress within the central gauge section, which persists until necking. This uniformity confirms we've created test conditions that represent the desired uniaxial tensile state along the hoop direction. Using the experimental force displacement curve as input to our training ANN, we simultaneously identified the key material parameters and the coefficient of section. The ANN training utilized the efficient Levenberg-Marquardt algorithm combined with early stopping to prevent overfitting, ensuring robust parameter identification. To validate these identified parameters, we performed a verification analysis comparing simulation predictions with experimental results. To validate these identified values, we ran a new finite element using the ANN combined parameters, the ANN determinate parameters, and the identified coefficients listed in this table. This low displacement graph provides our first validation of the identified parameters. The green curve represents the simulation prediction using our ANN identified parameters, while the red curve shows the actual experimental data. As you can see, there is an excellent agreement between the two curves throughout the entire deformation, confirming the accuracy of the parameters identified using our intelligent identification approach. Furthermore, we compared the resulting stress-strain curves to demonstrate the decoupling of a friction. This stress-strain comparison provides compelling validation of our approach. The red curve, labeled experimental curve, represents the apparent flow stresses derived directly from raw experimental data, which inherently includes frictional effects. The green FEM plus SCUF curve shows our simulations, including the friction matching the experiment. Remarkably, the pink ANN FM curve represents the true material behavior with friction effects removed, which perfectly aligns with the blue analytical HEAL 48 prediction using the identified parameters. This confirms our approach successfully isolates intrinsic material properties from testing artifacts. These results led us to several important conclusions about our methodology. So we have successfully developed them and validated two key methodological advances. First, a shape optimization approach for ring hoop tensile test specimen that achieves homogeneous stress-strain distribution for accurately hoop direction characterization. Second, an intelligent inverse procedure combining design of experiment, finite element simulation, and an artificial neural network model that accurately determines constitutive material parameters and friction coefficient simultaneously, effectively decoupling materials properties from friction effects. Experimental validation confirms the reliability and accuracy of both the optimized design and the identification method. These results significantly improves material characterization by isolating intrinsic material properties from extrinsic influences like friction. This enhanced accuracy enables more precise and reliable simulations of contact and friction heavily and friction-heavy applications such as metal forming, extrusion, and deep drawing processes. Furthermore, our methodology holds promise for broader applications in anisotropic material testing and could provide a foundation for developing standardized testing protocols for tubular materials which have been lacking in the field. Before concluding, I'd like to acknowledge the support that made for this research. We gratefully acknowledge the financial support for this research provided by national funds through the FC, the Foundations of Science and Technology, and also the Center for the Mechanical Engineering Materials and Processing at the University of Coimbra. Thank you for your attention, and I am ready to take any questions.